Hooke's law. Study of the oscillations or movements of an object attached to a spring is fundamental to the study of more general vibrating systems, such as shock absorbers in a car or landing gear in aircraft. Suppose a spring is held vertically by attaching one end to a fixed point. To the free end, we can attach an object. The weight of the object causes the spring to stretch. With different objects having different weights, the spring will stretch or extend to different lengths. Suppose we do an experiment by adding objects of various weights to the spring, and in each case, measure the extension. Let W stand for the weight added to the spring. Weight is measured in newtons. And let E stand for the extension of the spring beyond its original length. Extension is measured in meters. The measurements obtained are shown in this table. So, for example, when the object attached has weight 1.5 newtons, the extension of the spring is 0.06 meters, that is 6 centimeters. When there is no weight attached, there will be no extension. Each pair of values, weight and extension, can be represented by a point on the extension weight graph shown here. Note that this graph has more complicated scales than the ones we have seen earlier. The horizontal axis has a scale marked in intervals of 0.5. The vertical scale has intervals 0.02. Don't be put off by this added complication. Everything we have learned already applies in the same way as before. We have drawn a line through the points. Let us find the equation of this straight line. Here the extension of the spring, E, depends upon the weight attached, W. So E is the dependent variable and W is the independent variable. Because the graph is a straight line, we expect the relationship to take the form E equals m times w plus c. And compare this with y equals mx plus c. Now in this case, the graph passes through the origin, and so the vertical intercept, c, must be 0. The constant m is the slope of the graph. The equation becomes E equals m times w. We can use any of the other points on the graph to find the value of m. When w is 1, we know that the extension E is 0.04, and so 0.04 equals m times 1, or simply m, and so m is 0.04. Alternatively, we could note that a unit increase in the w direction produces a corresponding increase of 0.04 in the E direction. We conclude that the equation of the line is E equals 0.04 W. Using this equation, we can calculate the extension of the spring for other values of the weight. Finally, we'll introduce a few more advanced ideas. Don't worry if you don't follow all of this, it's intended to give you a flavour of where this goes next. As a consequence of the weight, there is a tension in the spring. It is this tension which causes the spring to revert to its original length if the mass is removed. it can be shown that the tension T is also equal to the weight of the object that is attached to the spring. So we could write our equation as E equals 0.04 T. In some practical situations, it is more helpful to have this expression in a form which tells us the tension in the spring for a given extension. So this equation might be rearranged as T equals E divided by 0.04, which is equivalent to T equals 25E. You may or may not know how to rearrange equations like this, but eventually you will. We see that the relationship now takes the form T equals Ke, where K is a constant, in this case 25. The constant K is known as the spring constant, and it will take different values for springs of different stiffness and different lengths. The equation T equals Ke is known as Hooke's law, after the English scientist Robert Hooke, who lived in the 17th century.